So yesterday we have seen that, today we're talking about a couple of things. So give further details about regularity issues for these double phase functionals. And these double phase functionals are characterized by the fact that there's a coefficient that regulates the kind of elasticity that you might have. So when the coefficient is larger than 0, you have a leading term which is which has Q growth, and Q is larger than P. And when the coefficient instead is 0, then you get a purely P Laplacian. So you get a switching of the type of elasticity according to a coefficient, and this has been widely introduced by some Russians in the 80s, like Zhikov and other people, because they wanted to give a model for strong anisotropic materials and Paris situation. So, as I pointed out yesterday, here we have features of functions with a weight, because A of x is in a sense a weight, because when the weight disappears, then you lose ellipticity, but you lose ellipticity in a way that you retain the P ellipticity, and when A is larger than 0, then you have a phase transition between P and Q. So therefore, everything, the whole game is about the zero set of A of x, because the zero set of A of x regulates the transition between the two kinds of ellipticity. So this is an old theorem we proved with Diego Fonseca and Jan many years ago, and this tells you that there's an interplay between the regularity with respect to x and the two exponents. And this tells you that if you do not have enough regularity to compensate the way the two exponents are far from each other, then you can have surprisingly discontinuous minimizers on a bound on a set of maximal Hausdorff dimension. And we recall you that a minimizer is in any way a W1P function because it makes the energy finite. Therefore, it's the set of the essential discontinuity points cannot exceed n minus p. So this is telling you that everything goes as bad as it can, because a minimizer, which is usually more regular, is as bad as essentially any other competitor. So this is the condition, and then yesterday I showed that in recent work together with Maria Colombo, we proved that this condition is actually sharp for regularity in the sense that when this condition is not satisfied, you can have the du is Hölder continuous, and this is optimum, both with respect to the condition and with respect to the kind of regularity we're using, because, of course, Ralston's theorem tells that when, for instance, A of x is completely 0, then you have a minimizer of the P Laplacian functional, and you get the maximal regularity of solutions. On the other hand, if you look at the counterexample, this was the condition. So the condition tells in particular that Q minus P is strictly larger than alpha. And it's not only formulated in terms of a ratio, but it's formulated in terms of a distance. And in the counterexample, minimizers are bounded. So minimizers belong to L infinity, but does not belong to C0. So you might wonder if there's another theorem that takes into account bounded minimizers and deals with regularity when this condition is not satisfied. And this is actually the next theorem, again with Maria Colombo, that tells you that if you start from an a priori assumed to be an a priori bounded minimizer, then the condition actually becomes this one, and this is absolutely sharp, because this is essentially the complementary condition to the counterexample. The techniques for proving this theorem are rather delicate, because you have to essentially at each stage to calculate the interactions between the two averages. And I'm going to give some ideas of the proofs, but the proofs are rather long and cannot really be sketched in a concrete way at this stage.
The du is Hölder with what exponent?
Some exponent. Okay. That even when A of x is 0, the theory tells that there is some exponent, which in general is conjectured to be at least 1/3. let's say there's a lower bound. For sure, it's not every exponent. There are counterexamples by Urels. So when you reach, essentially, we can say that it has more or less, it is essentially the same exponent of the P Laplace, or something like that. But this is at this stage not really related to this problem. It's a different issue. Okay. Okay, and in particular, these two theorems paved the way for the first really strongly anisotropic example of nonlinear Calderon-Zygmund theory for non-uniformly elliptic operators. Because as I remind you, the idea of this why these functionals are interesting, because they are anisotropic examples of non-uniformly elliptic operators. Yesterday, we saw that there's this famous theorem by Ivanets that tells exactly that if you have, this is Ivanets, Tadeusz Ivanets, 83, that if you have this problem, this equation, where the right-hand side is written in this peculiar way just for aesthetic reasons, because you want to have a sharply and nicely looking statement, but you can actually have, by change of verbal, any divergence statement. Yeah. Okay, then Tadeusz Ivanets was able to prove that if f belongs to LQ for some q larger than p, then the gradient belongs to LQ for some q larger than p. So this is the starting point of nonlinear Calderon-Zygmund theory. And of course, for p equal to 2, this is exactly Calderon-Zygmund theory. Okay, and now we are able to extend, to give, let's say, one of the very first examples for which nonlinear Calderon-Zygmund theory can be extended to non-linear and non-uniformly elliptic operators. And this is exactly the same theorem. So the idea is that you cancel, you delete, you simplify the divergence operator, and then you expect that the natural quantity appearing on the left-hand side is exactly where the natural quantity on the right-hand side is assumed to be. And also the proof of this is rather delicate, and you see that if you start for any distributional solution with, let's say, natural energy assumed to be bounded, then you get this general thing that takes into account, the interaction between the two exponents q, p, the dimension n, and the rate of regularity, let's say the rate of phase transition of the coefficient. Moreover, if you assume that the solution is a priori bounded, then you can get rid of the dependence on n, and then you can get exactly as the counterexamples tells you. There's an additional, probably technical assumption that we need this other quantity to be a suitable Morley space. That's the idea. But this is not very unnatural. Why? Because if you make the computations already when L of x is 0 and or p is equal to q, let's say in the classical case, then you see that there's no reason for solutions to be bounded if this condition is not satisfied. Let's say this condition is the one that comes into the play if you want to prove a priori that a minimizer or a solution is bounded. Of course, you might still say, I assume that a minimizer is bounded, or a solution is bounded, and then I want to prove this for any solution. No, we still need this technical assumption that doesn't look too dramatic to humans. Okay, these functionals and this. By the way, one thing, this theorem is holds not for any distributional solutions, but for minimizers of these functions. And let me observe that the Euler-Lagrange equation of this functional is precisely this one. We need the minimality. We need more minimality to prove some denseness. The proof is delicate. Okay. Okay. So what's the idea between this, between the lines and actually behind the scene is that essentially all these functional they have a richer structure that takes into account the combination of the two as a whole replacement and as an intrinsic replacement of the p node. Let's say many results can already be obtained by any functional that is not controlled by z to the p and z to the p, by just buying this new quantity. And then inside you can put whatever you like. So the idea is that essentially it's like in the Muckenhoupt weights or in the degenerate operators and so forth. There's a new quantity playing the role of a norm, and then this becomes a new intrinsic quantity that you might want to deal with. And essentially, this is essentially you encode the features of this. Let's say degenerate double phase. This degenerate transition. Let me now say something about the occurrence of these conditions. The occurrence of these conditions. So why these conditions are satisfied, have to be satisfied in order to guarantee regularity. In particular, let me say something about the counterexample we built with these people. The counterexample is based on a cone-type construction that also finds similar analogs in the theory of Muckenhoupt weights. And in fact, as I was explaining yesterday, there are clear connections between these kinds of things and theory of Muckenhoupt weights and the generate elliptic operators of the same kind. Okay, how did we build the counterexample? We take a ball, and for instance, take in 2 dimensions, and we make a cone. Okay, in this cone, we make the Q phase live in the upper and the lower part of the cone, so in the vertical cone. So this is the Q phase, and this is where the coefficient is living. Your coefficient is living. So here you essentially see Q in terms of pure growth. Here we make a coefficient which is 0. So here you see the P phase. So that's the P cone. Okay, then what you do, you take a boundary value which is very large here, let's say a very large constant here. And here it's minus m, so it's very large, but it's negative. So, and then you connect it radially. Okay, you go from m to minus m in a radial way. Connecting in a fine way. Okay, then you solve the Dirichlet problem with this boundary datum, the 0, u0, it's this one. And then what happens? It happens is that when you're going to minimize this energy, so what's the point here? The point is that you have to go from m to minus m. So if m is very large, you pay a lot of energy, right? You pay a lot of energy. Now, since q is larger than p, you might like to prefer to do the whole balance, not in the q phase because you pay a lot, but just in the p phase. So if q is too large, with respect to p, there's no reason for the minimizer to prefer spending energy in the q phase, but you prefer to spend all the energy in the p phase, so you decrease the energy because you tend to minimize things. So you tend to be constant here, and then to do the whole job here. But in this kind of minimization process, what happens? That if you tend to be constant here, you will be m here, minus m here, plus m minus m, and then you have to do the whole job for an m large in a smaller and smaller thing, and then eventually you create a smaller. On the other hand, how is the coefficient done? The coefficient is something like x to the alpha here. Now, if there's x to the alpha, what happens? That this kills the energy. If this multiplies the q, right, this kills the energy. So you might still want to make your path here not to be constant, so you decrease the singularity. You can decrease the energy also in the q phase. So essentially the role of this weight is to kill the q phase and to make it appear as the p phase. And essentially this is the condition. The condition for the regularity is that the q phase is compensated by these two things. That's the idea. This is the point. In fact, you can also see this condition in a different way. Yesterday we saw that the rate of non-uniform ellipticity determines the lack of regularity of solutions. So the ratio between the highest and the lowest eigenvalue in the elliptic problem tends to diverge is a clear obstruction to the regularity of solutions. And now we see an interaction between the two objects. Okay, now let's put in a ball of radius r where a of x touches 0. Since a of x is assumed to be let's say, to be Hölder continuous, this means that a of x is more or less r to the alpha in that ball. Okay? R to the alpha in that ball. On the other end, you see that what you want to prove is that the gradient is bounded to prove regularity. So Q minus P tends this ratio to be divergent when du goes to plus infinity. On the other hand, this tends to kill the whole stuff exactly as in the counterexample. If this kills enough growth of this, then you stay with the regularity. Otherwise, you blow up. So you can clearly see the occurrence of these conditions when you look at the ratio between the eigenvalues. The ratio between the eigenvalues determines the rate of non-uniform ellipticity of the problem. So if the ratio is too large, then you lose regularity. So there's the interaction between the coefficient and the growth condition. That's where it comes from. Another probably better way to frame this phenomenon is the following one. You know that a way to measure the kind of regularization and extension properties of solutions is to measure the P capacity of a set. Measuring the P capacity of a set means that you are essentially computing the energy of a so-called P condenser. So that's the infimum, that's the least energy that you spend from going to from 1 to 0, essentially. That's the P capacity on a set. Because this is the P capacity of a ball. Okay, then you may extend it the P capacity of every set. And P capacity is connected to the kind of extension and the regularity properties of solutions. For instance, you can extend solutions outside an open subset when the P capacity of a solution is 0 and so forth. Okay, the P capacity of a ball is this one. The P capacity of a ball. Then you can consider a different capacity. And let me now consider a ball centered at 0, exactly as in the counterexample. Now, this is a weighted capacity of the type very much considered by, for instance, by Mazziani. If you go to Mazziani's book, and there are plenty of papers with different capacities. Okay, this capacity is nothing but it's just the same concept, but changing the energy. Okay, you're just changing the energy. Okay. Now, it's not difficult to understand that if the P capacity is n minus P, then if there would be nothing, you would get n minus Q, otherwise you put alpha here. So you kill the bit, right? Okay, so now you have essentially two capacities, two different capacities, the P capacity and this weighted capacity. On the other hand, the functional you're considering is combining both. So the functional you're considering is combining both the capacities, because it's this one. Now, assume that you have a singular point. When a singular point, for instance, cannot be removed. A singular point cannot be removed, for instance, when it has positive capacity. So essentially when P is larger than N or Q is larger than N. So if you go to the example, and if you go to the Q cone, you see that the Q cone for Q, large in particular, large than N, then at this stage you can see the point. So from this cone you can see the point. Okay? On the other hand, if P is less than N from this cone, you cannot see the point. So in other words, you have two different capacities, and if these two capacities, they are talking to each other, then you create a real capacity, and therefore you create a real problem. Elliptic problem. Otherwise, you can expect singularities, because one part of the energy sees points that the other part is not seeing. Okay, so we have two capacities, and then you might like to see when this capacity, which is a priori larger than this one, is controlled by the other one. It's very simple. Then you prescribe that this is less than or equal than this, and then the condition is exactly the one rest. So the condition is actually a capacitary condition that tells you that there are two capacities, but these two capacities actually coincide because they see the same sets. And if they see the same sets, so the problem is, in some sense, well defined from the point of view of regularity. That's the idea. I think there's a lot to do on these kinds of functionals and on more general structures involving more, different types of elliptic operators. Every number of years, we see new elliptic operators coming up that retain some properties of old ones plus new features. For instance, now it's the time of fractional operators, but now there are also other directions because now you can play with different rates of degeneracies. Still being local, but still got completely new phenomenon in this setting. Okay. Further analogies, for instance, with Muckenhoupt weights. Okay. Remember that Muckenhoupt weights are, by now, very classical object. And these are essentially the weights that were introduced by Benjamin Muckenhoupt to answer the following problem. When is the maximal operator bounded with respect to a weight? Then the condition is that the weight must be so-called Muckenhoupt weight. So there's a certain condition. Okay, the problem was the following one. For those who is not remembering at the moment, you know that the maximal operator being bounded, that's the classical Adi-Littlewood theorem, tells you that you can control the maximal operator of a function to the p by f to the p. Okay, what happens if you put a weight here? So you consider a weight at space. That's this tells you that this has to belong to the Muckenhoupt weight. And then eventually, Fade-Skin and Serapiomi showed that if you have Muckenhoupt weights, then everything works because homologue quantity applies, and then you can start with the usual procedures of regularity. That's the whole story of leading to. I think that these Muckenhoupt weights recently came back into the play. I mean, for young generations, when Caffarelli and Sylvester reduced the study of the fractional P Laplacian by extension, and they lifted and then they did Muckenhoupt. I think that this was a very natural fact, especially for masters like Caffarelli, because for people of that generation, this Muckenhoupt were, everybody was dealing with these Muckenhoupt weights. So this was a very nice connection they showed up with. Okay, anyway, that's an analogy with Muckenhoupt weights, and the analogy is exactly the same condition that I showed you before for general minimizers. Let's say Q over P is less than 1 plus alpha over n, then this is a sort of Muckenhoupt condition, and then the same condition allows you to prove a maximal theorem. Let's say that you state that with respect to this new intrinsic norm that takes into account all the growth and mix them up with the weight, which is A of x, then the maximal operator is bound. It's essentially the same phenomenon. And in fact, if you want to prove the necessity of Muckenhoupt weights for regularity of solutions, you make also constructions like this of the following type. So that's the analogy, and then further analogies carried over by Sobolev-Poincaré of this type, and so forth. In particular, once you have Sobolev-Poincaré, you can redo the Georgi-style iterations, and then you can get regularity for minimizers and so forth. This is part of the observation made. This is essentially the definition of Muckenhoupt weights. And you can see the perfect analogy. That generate equations with Muckenhoupt weights have regular solutions. This is connected to the maximal operators, to Sobolev-Poincaré inequalities, and so forth. And then you see exactly the same analogy that between these operators and this the classical Muckenhoupt operators. Here, the difference you see, Muckenhoupt in the classical degenerate operators, you have, let's say, degenerate functionals of this type. You have a of x due to the cube. So when a of x is 0, nothing remains in your hands and you lose everything. Here, when a of x goes to 0, you still have a different rate of degeneracy. So you switch from two different degeneracies instead of switching from one degeneracy, from one ellipticity to 0. Here you switch from two different ellipticity of two different orders, while in the Muckenhoupt case you switch from one ellipticity to nothing. Let's say that's great. And in some sense, this should be read as a sort of Muckenhoupt condition. And of course, you can take this problem as a paradigm for many other elliptic problems that have different degeneracies. You see, when you have a degenerate operator, now you can also play with the degeneration. It's not only the structure. And in particular, I conjecture that you can define, related capacities. You can define, you can redo a lot of the standard theory under these conditions, and with more or less following the path of these kinds of things. This is the kind of things, but it would be interesting, in my opinion, to take this as a paradigm for more general degenerate problems where you have different ellipticities coming into the play according to a phase transition. And then you could also essentially get these models to combine with other things and to get other results. The basic two theorems are in these three papers with Maria Colombo. Actually, there are three papers because these are, the first theorem is in a paper on ALMA. The second theorem is in a paper on ALMA, but they're not the same paper. It's two different papers because they're very long. Okay, and I think that this. Okay, now a few words about the proofs. So essentially here, the idea is that we have to build up regularity, understanding in which phase is the problem. Okay, and so that's what. Okay, I'm actually, for expressing elliptic regularity, what I'm saying is rather natural. There's a whole list of elliptic problems where you have essentially more phases. For instance, if you take the Mumford-Eschat functional, then you take, there's a bulk term plus a perimeter term. And you tend to minimize both. But then the minimizer always chooses a phase. Let's say if you are in a bulk term, then you stay in the bulk term and the other one is not there. Otherwise, if you see the border of the image when you reconstruct the image via the Mumford-Eschat functional, then you just need to jump, and then essentially the bulk term is essentially not counting there. So we believe that if some regularity is there, then it must be reached via a similar phase transition. So the idea is that if a of x is small enough, although this term has a larger growth, contradicting every orthodoxy, this term becomes a perturbation of this one. Usually, the lower order terms are characterized by having a lower exponent. Here we do the other way around. Because if we look at the counterexample, in the counterexample we see that there's no singularity because the weight is killing part of the cube. So the idea is to look the other way around and to see the term showing a larger growth with respect to the gradient as a perturbation of the other. But this will happen only after as a certain universal threshold level of the weight. And so that's how it goes. There's a universal threshold such that if the inf is smaller than r to the alpha, so if you are thinking of the counterexample really in this situation, then essentially this term in the minimization process becomes a perturbation of this. You see, you cannot a priori see this easily, because if you rescale the functional in the gradient variable, you will have something that blows up and so this dominates. This you have to do at every scale.
You don't want to say the soup is less than that.
No, the inf. It's better to do with the inf.
But that's easy to achieve.
They are the same, because the functional is Hölder continuous. And if the functional is Hölder continuous, inf and sup, they differ by r to the alpha, and then they are essentially the same. But if you do with inf, essentially you can do it with the sup. Exactly for the reason I told you. But if you do it with the inf, it's more elegant, because essentially if you contradict this, then this stays contradicted also for the smaller scales.
Oh, sorry, I see what you mean.
Yeah, right.
Yeah, no, sorry.
Okay. So that's the idea. So we shall take a ball, we shall check this condition, and if this condition is checked, then the functional will behave like due to the p, and since minimizers of due to the p are regular, you can take advantage of this fact, making a suitable comparison arguments. If on the other hand, this condition is not satisfied, you say, okay, then I have Q growth conditions, and then I only use the Q part. That's wrong, because although you have Q growth conditions, this guy can be still small. But it's small, but it's not small and after rescaling with respect to the Hölder now. That's the point. You have to rescale with respect to the Hölder now. So you still have to use both. But the good idea is that now you have a structure with constant coefficients, and this structure still have these kinds of structures still have regular minimizers. So in the two cases, you are able to play with the thing. How do you define? So let me give you, for instance, two tools that you can easily get. Okay, not easily. The second is more easy. This takes 15 pages actually. Okay, for instance, take a minimizer of this functional, and take a ball where this condition is satisfied plus this. Then surprise, surprise, you have a reverse Hölder inequality. Now you say, okay, but this is the usual reverse inequality. Actually, it's not. Why? Because reverse inequalities, as we saw yesterday in parabolic problems, are homogeneous. And you cannot get homogeneous estimates if the problem is not homogeneous. This problem is not homogeneous because this case like P and this case like Q. But it becomes homogeneous only on that scale by the interaction with the radius. In fact, what we prove here is that if you would have just due to the P, then this would hold for any subball. But this holds just for that ball where this condition is satisfied. So this doesn't tell that this holds for every ball. This tells exactly that it holds only for that ball. And eventually you can recombine this in an alternative scheme. Because it is usual when you deal with regularity with standard growth conditions, that if you have, for instance, a minimizer of a functional with P growth, let's say a minimizer of a functional like this, and f x dv is like dv to the P, then what do you have? You have that du, there exists some exponent P plus delta, 1 over P plus delta less than or equal due to the P. This is B rho, this is B2 rho, and this is for every P rho in the domain. There is a so-called Gering's lemma. But here, you see, this is an homogeneous estimate because the functional is homogeneous because this can be controlled and is controlled by dv to the P. But this holds for every pole. This doesn't tell that this holds for every pole. This only holds on those poles where this condition is satisfied. So there's an interplay. So this tells essentially that the second part of the functional can be reabsorbed in the first one. It's like having a standard growth function. This is what you get. So this is a first sign that under this condition that we call the P phase, the functional commutes and becomes a P growth function. A second tool, for instance, if you get a bounded local minimizer, then you get that if you are in a ball where you have this condition, you get the standard Caccioppoli type inequality. Caccioppoli type inequalities are those inequalities where you can control an a priori higher order object as a gradient with the functional itself. Once again, this is standard for functionals with P growth. It goes back to the work of Giuseppe Mingione. back to the beginning of the 80s. And this holds for every ball. This tells once again that in some sense the problem shows exactly the same features of the P-growth problems. And essentially these are two tools that you can eventually combine to prove regularity. How will you prove regularity? Then making alternatives. For instance, when you want to prove that a minimizer is Hölder continuous, you will do, as very often you do, you take a sequence of shrinking balls. You want to prove that the oscillation is decreasing geometrically. Then you take a ball, let's say B, Ri, and then you say, is the first alternative, let's say the P phase satisfied on BRI? Yes, then you use these kinds of inequality, and then you shrink on the first ball. And then you go and you wonder yourself if this condition is satisfied at each stage. At the first stage, that's the exit time where this condition is not satisfied, you will enter the second condition, and once you are in the second condition, you are always there. Because it's easy to see that if the inf is larger than a certain constant for certain radius, then when you decrease the inf gets larger, and the constant gets smaller. So once you are in the, let's say, Q phase, you are always in the Q phase. That's the way you do combine the two things. And that's exactly the same thing that happens for problems like Manfred and Shah problems and blah blah. At the first stage, there's a smallness condition on the jump, then you are always in the situation where the image has a real jump, and then you actually use the minimal surface theory. That's how you prove regularity of Manfred and Shah problem. Regularity of Manfred and Shah problem, if you think of reconstructing an image, then you look at a small ball, and you see if there's that's essentially the classical proof of the Giorgi, Carrera, and Leaci. If you are in a small ball, if there's enough jump, then essentially you are in a situation where you really reach the border of an image, and then in order to prove regularity, you use the regularity of the inlet surfaces. Otherwise, if you are far from the image, let's say you are here, the jump is so small that can be smoothed out, and therefore you are just minimizing the quadratic functional, and therefore you are in the regime of harmonic functions. And you use the regularity for harmonic functions. There's a similar case to analyze. Okay, that's the second. Okay, but this I would like to advertise a bit that these problems are really new, and there's really a lot to do for these kinds of operators and problems. And now we go to the next part. That's measured data problems. Okay, you can remember that in the first lecture I was talking about Hölder and Sigmund theory and nonlinear potential theory. Here we really enter the core of nonlinear potential theory with potential estimates. And then I was considering operators of this type, like for instance the P Laplacian, with the right-hand side being something. And the situation where we have considered is like P growth. And the situation considered up to now was that this guy belongs to the dual of the natural Hölder space. Now we want to understand what happens when the right-hand side does not belong to the dual. And that's the case of measured data problems. So the right-hand side, which is equal to a measure. Of course, solutions must be properly understood in which sense they hold. And I will consider problems of this type with P growth and with monotonicity assumptions. So nothing different, nothing, spectacular. These are the standard assumptions. So if you just want to simplify your life, you can think of the P Laplacian operator times a coefficient equals to a measure. Yeah. And we solve the Dirichlet problem. Okay, the case P equals to 2 is a very classical work by Littmann, Stampacchi, and Weinberg. They define solutions by duality. I'm not going into that. First of all, you can define distributional solutions in the usual way. And let's see, what do you need for defining distributional solutions? Here, nothing, because you can always if this is a Borel measure, any C-infinity function. It's okay. Borel measure is a distribution. For the right-hand side, you need a bit more. You need that this guy is in L-infinity, so this guy must be in L1. And essentially, if you look at this guy being in L1 means that U belongs to 1p minus 1 at least. This is called a distributional solution, and in particular, since it does not a priori belong to W1p, it's called a very weak solution. So a very weak solution is a distributional solution that does not belong to the natural energy space. They do exist, in fact. Okay, how do you prove existence? Actually, by the usual method, you prove existence of distribution of, let's say, classical weak solutions. There you do Galerkin. Here you do Galerkin over Galerkin. You take a sequence of approximating functions. For instance, you take the measure, you smooth it out by a sequence of modifiers. You can solve these guys, and then you prove a priori estimates, and then you go to the and you can prove this actually. And this is a basic contribution by Boccardo and Galloway at the end of the 80s. Boccardo and Galloway. Okay. These solutions are the solutions for which you know existence, and these are the solutions that we are considering. See, these are called solutions obtained via limiting approximations, and these are called SOLA. So from now on, I'm not considering any distributional solution for which very little can be said, because you see, you lose the property of being an energy. But I'm just considering these solutions obtained by limiting approximation. Okay, actually, there's a nice story about this name of this SOLA, because it's a triple joke. Why these SOLA were introduced? Well, they were introduced not only because they wanted to solve the problem, but they wanted to find a class of functions for which you can uniquely solve the problem. And this is still an open problem. In fact, you can prove that SOLA exists, and this is not difficult, but uniqueness of SOLA is still an unknown fact. So this is one of the main open problems in the theory. It's amazing that, for instance, for such classical problems, there are so many open issues. So people sometimes should also look at more classical stuff that sometimes are not dealt with, not because they are old and forgotten, but just because they are too hard. That's the point. Okay, the triple meaning is the following. SOLA can mean solutions obtained by limiting approximation, but in Italian means also sola. That means lonely. Let's say unique. But at the end, they turned out to be insufficient to prove uniqueness. So they became sola. That in the Roman dialect means something that promises and then doesn't keep the promise. So it's something fake. So that's a triple joke. So you say in one game a destiny. So the destiny to be the only solution, and then the destiny of, not promising, not achieving the things you were devised for. Okay, the model problems are these ones: P Laplacian with coefficients, and also with dependence on it. Okay, in fact, solutions are not in the usual energy space. This is called the nonlinear Green's function, and essentially for p equals to 2, this is the usual Green's function. Otherwise, you can make computation. It's a distributional solution to this problem. Well, this is the Dirac mass charging the origin. Dirac mass means that the measure of a set is 0 if it doesn't contain the point, otherwise it's 1. And this is apparently, this is in terms of integrability and regularity, the worst possible solution, and ironically is one of the very few cases where uniqueness can be proved by other means. This is important because then if you want to test your regularity problems, Okay, the optimality of your regularity problems, you can compare with the properties of this nonlinear space function. A list of people who worked on this, Boccado and Galloway, then there's the Finnish school with very beautiful results I'm going to talk about largely later. Greco, Ivanez and Sbordone, Fiorenza and Sbordone, Holtzman, Ungenbuller and Muller in a series of papers, they dealt with the vectorial case. Okay, all in all, large part of the literature is dealing with the integrability of the gradient, and they were essentially proving this regularity result that due to the p-1 belongs to this Marcinkiewicz space. Marcinkiewicz spaces, as we are going to see in a few minutes, are the natural spaces where to look for regularity in terms of integrability for these kinds of problems. These types of regularity is revealed to be optimal by the fundamental solution. Okay, Marcinkiewicz space. What is a Marcinkiewicz space? F belongs to M gamma if the decay of the level set is not usually measured by an integral, as in Lemay spaces, but just by a suit. That's Marcinkiewicz. Marcinkiewicz spaces are the right spaces to measure potentials. Why? Because if you have a potential like this, you know since first year that this doesn't belong to L gamma. But it belongs exactly here. Because there's an infinite scale of logs that are missing, and this infinite scale of logs is in limiting case measured by Marcinkiewicz. They refine Lebesgue spaces because they are slightly larger than L gamma, but smaller than all the previous ones. These are special cases of another class of function spaces that I'm going to talk about. These are Lorentz spaces.
Are we assuming finite measure?
Huh?
We're assuming we're on a finite domain, right?
We assume that.
Rn.
Okay, never mind.
This is Rn.
This is Rn, yeah. Rn. We are in Rn. We are in Rn. And essentially, this is the type of function you have to think of when you think of Marcinkiewicz spaces. When you think of functional spaces, nowadays, the absurd sense delirium is that you define a function spaces as many times as you like, but without having concrete models in your mind. Function spaces are just something that you define after you have a model in your mind. For instance, Marcinkiewicz are suggested by potentials of these types, and you see Lorentz spaces are perfectly natural because after powers, you know that there are logs, and Lorentz spaces, they encode logs. Okay, where does the definition come from? For instance, by Chebyshev. Assume to get an L gamma function, then you can estimate this in this way. Then you can plug this on, and then you can get this inequality. Just pretend, without knowing this, that the left-hand side is finite, and then you get Marcinkiewicz. This is a way you can easily get the definition from. So it's a better way. It's a lighter way to measure the decay of the level set. You are not summing. You are just taking the soup. This is a small empty spaces. Okay. In particular, okay, this is the optimum integrability if the right-hand side belongs if the right-hand side mu or f belongs to a Marcinkiewicz, then this improves accordingly. So in particular, we can also wonder for solutions of this type, what are the functions f for which this belongs to the dual of the double Sommler space, and this is exactly the borderline exponent. This is the duality exponent. Because you know that a function for belonging to the dual of a Sommler space, you have to make finite this duality, and this belongs D to W1P. But if it belongs to W1P, then you know that this belongs to LP star, and LP star is NP over N minus P. So this, in order to belong to the dual, must be in the dual of the sublet conjugate. So if it's in a worst space, then it's below the duality. And this is precisely the duality exponent. So the things I'm going to talk now is about when when f doesn't belong to the dual case, and in the worst possible case, f is a measure. F is a measure. Okay. Now a theorem that I proved many years ago that tells something about a certain form of duality that there is when you do consider the geometry of the measure versus the integrability of the solution. So the general idea that this theorem is telling you is that the geometry of the set where the measure is concentrating determines the integrability of solutions. Measures are not like functions. You do not have to see their height. You have to see the way they concentrate. Looking at how a function is large determines tells about integrability, but here you have a measure. So for the measures you have to see where you do concentrate. So in the Dirac case, there's the worst possible concentration because all the mass is considered in one point. And so you prove that U belongs to the P minus to this Muckenhoupt, and this is optimal by the Green's function. Okay, what happens if the measure starts spreading? For instance, if it spreads on a set with Hausdorff dimension n minus theta, quantitatively. Essentially, you can create as many measures of this type by using Frostmann's lemma. Frostmann's lemma tells that if you take a theta capacity zero set, then closed set, then you can construct a measure that has its support over there and has mass equal to 1. Okay, if the measure is concentrating on a set of n minus theta, this tells that the concentration of the measure is that the Hausdorff dimension is larger than n minus theta. Then the solution improves accordingly. So the more the measure spreads, and the better the solution is the solution becoming. Because essentially, the idea is that if a measure concentrates on a very single point, then the solution tends to be very good in many places and concentrates all the bad behavior on a very small set. Therefore, you can put everything in height, and therefore the integrability gets below. But if the measure spreads, if the measure starts spreading, then the solution improves. Because you cannot be a solution blowing up in too many places too roughly simultaneously. That's the idea. So this tells that quantitatively the measure cannot concentrate on sets of Hausdorff dimensions smaller than n minus theta, and therefore the integrability of the solution improves accordingly. So you see, the smaller theta becomes, and the more the measure is spreading, and then the better the integrability becomes. So that's a duality. In particular, when theta is 0, you get any measure, and for when theta is equal to n, you get any measure, and for any measure you get back to the classical result. Otherwise, you get something which is intermediate and gets better and better as theta decreases. In particular, when theta goes to p, you will get that you are in Muckenhoupt p. You are almost in the energy case. So for theta equals to p, then the gradient belongs to Muckenhoupt p, so you are almost in the energy case. On the other hand, why I did not consider lower values of theta, because for lower values, this condition tells that the measure is in the dual, because it is not charging p capacitary zero sets, and therefore for a measure in the dual space, you can find usual energy solutions. I told at the beginning I want to deal with the non-energy solutions, and so this is the density condition that is telling you it's a dual condition. This contained in this old paper of mine. Okay. And what about the parabolic problems? Okay, for the parabolic problems, there's a theory constructed by Boccardo, Dallaio, Galois, and Orsina, and you can essentially redo the same things, but in the parabolic setting. And then there's a very recent theorem, which is a deep result of Paolo Baroni, that extends this principle to the parabolic case. And this is now very much more delicate. Why? Because now you're dealing with the p-parabolic problems. As we saw yesterday, p-parabolic problems, they need to be considered together with their intrinsic geometries that were introduced by Di Benedetto in the 80s. And now you want to match a condition, a density condition, which is satisfied on any parabolic cylinder, only on parabolic cylinders. And then you want to translate into regularity, but then you have to go through intrinsic geometry. So you have a condition that is satisfied only on standard cylinders, but then you have to use intrinsic cylinders. And getting the two things together is not very easy. Essentially, you're dealing with Morris spaces in p-parabolic problems, and this was, in fact, the proof is really non-trivial. So this is the first result I wanted to talk about when dealing with measures. And the first result essentially is telling you that the integrability improves according to the non-concentration of the measure. So, geometry of concentration versus integrability of solutions. An interesting fact is that this exponent is for every theta sharp. This follows by classical theorems of Serrin in the 60s. Why? Because, okay, assume that the gradient is better than this, so that this result is not sharp. And already for p equals to 2. If the gradient is better than this, then also U improves its integrability accordingly. Let's say U is in a certain L gamma space. But then Serrin proves that if you have a solution of a certain problem, let's say in an open set less than a certain compact subset, and this solution has this integrability, then you can, let's say remove the singularity. This is the singularity removal. Okay. Now, by Frossman's lemma, you can consider a measure that concentrates exactly on a house of on a set of houses of dimension n minus theta, and has this property. So you can get a measure here. And this is everywhere. So you solve this problem everywhere. But if you solve this problem everywhere, in particular, you solve this with 0 outside the compact set. But if you have this integrability, then you can prolong the solution everywhere. But if you can prolong the solution everywhere, then this measure is not there. And this is not true. So you cannot go beyond this integrability. And L gamma is let's say, gamma is the Q star, Sobolev embedding, and Q is larger than n minus theta, p minus 1. So this is telling you that this result is sharp. So there's this is one of the two results I wanted to present for general measures that tell you about something, the integrability of the measures. Okay, the second result is actually more interesting because it deals with something which is very, very common these days, and these are fractional Sobolev spaces. Okay, what is a fractional Sobolev space? There are infinitely ways you can say what is a fractional Sobolev spaces, and there are infinite many editions of fractional spaces. Calderon spaces, Nikolsky spaces, Sobolev-Slobodevsky spaces, Gesov spaces. Whatever you like, there are, I mean, that's the definition of fractional spaces. Okay, these are called Sobolev-Slobodevsky spaces, and they can be described via the so-called Gallardo norm. Okay, the Gallardo norm in this quantity, and this tells exactly that you want to measure the oscillations of V using the L gamma norm. If these oscillations in L gamma are small enough to compensate the blow-up of this kernel in a way that this is finite, then you are in Sobolev spaces, WS gamma. See, this is blowing up, and it blows up more violently if S gets larger. So by scaling properties, you can intuitively think of an S derivative here, just by using the scaling properties that you would expect from a local definition of an S derivative that nevertheless does not exist. So these are Sobolev spaces, and they have their own fractional embedding. I think that nowadays this is very common. When I actually proved this theorem, these spaces were known by essentially nobody. And now they are coming back for this fractional problem. Okay, and now I'm considering general operators, but think back again to the general P Laplacian operators, and now I'm prescribing a bit more of differentiability. I'm prescribing that this is also not only growth conditions with respect to A, but also differentiability. These are once again a prototype assumption satisfied by the P Laplacian condition. Okay, the idea is the following one, and this gives actually the borderline case for measure data of the Calderon-Zygmunt theory. This is the first borderline case of Calderon-Zygmunt theory. So in particular, what I'm talking about is non-trivial already for P is equal to 2, because here is not, the point is not passing from to the generic problems, it's passing from linear to nonlinear problems. Okay, the gap of the theory where I dealt with these problems, and let me just start for the case P equals to 2, was that on one end, if you do consider these equations, then you can prove that the gradient belongs to Marcinkiewicz n over n minus 1. So you know everything about the integrability of solutions. On the other hand, Calderon-Zygmunt theory tells that already in the case of the Poisson equation, you cannot expect that the gradient is in W11, this phase. A way to see this is that this impacts into Ln over n minus 1, and the fundamental solution is not there. Okay, on the other hand, this is not, on the other hand, as soon as this starts being in L plus epsilon, then this is true. So the idea is that there cannot be a complete lack of differentiability when epsilon goes to 0. So you start from 1 differentiability to 0. And so the result I proved many years ago is that essentially you are, if you cannot be in W1, you are in every space before. And this comes together with a Caccioppoli type estimate. In fact, this comes back together with a Caccioppoli type estimate that at the same time was used by me to prove a few potential estimates and to start at the Giorgi fractional iteration. At the same time, I discovered that then Caffarelli, Basser, and other people around were using similar to Giorgi's fractional iterations to prove regularity of solutions to fractional problems. So this will be discussed tomorrow. Okay. Anyway, this is the borderline case of the measure data problem space. And the proof is rather delicate and involves a certain construction that reminds, that can be thought as a sort of nonlinear atomic decompositions using ideas from let's say, decompositions of fractional spaces using atoms. But these atoms, while in the standard cases are considered to be harmonic functions, here are considered to be not harmonic, but solutions to nonlinear operators. And then you do this nonlinear Calderon-Zygmunt. And this is essentially the Caccioppoli estimate I was talking about. Here you get the fractional norm. So in a standard problem, when the right-hand side is 0, you will get second derivatives estimated by the gradient. Here you don't get second derivatives, but you get almost second derivatives estimated by the gradient plus the measurement term. Tomorrow I'll show you also a version of this inequality on level sets and truncations with which you can start the Giorgi fractional type of iteration. And this is the theorem. Okay, what happens when this is the case for p equals to 2? So for the p equals to 2, you get exactly what you would expect. Okay, what to expect for p less than 2? For p less than 2, let's make the following heuristic. When 1 over x to the beta belongs to S gamma, computations, this is the solution. So now you remember that the solution of the fundamental solution is like this, and then if you want to get the gradient, which is now in W, something, and then you fix this exponent to be p minus 1, which is the mean of the integrability exponent, then this yields, you would expect that this belongs to this, below p minus 1. So this is the conjecture. This is satisfied by the nonlinear strings function, and this is in fact what you can prove for every p less than for every p down to with essentially the same method. I just told first the case p equals to 2 because I mean it's easier to frame, but otherwise you get this. And this, in a certain sense, fills the gap. Fills this long-standing gap about the maximum regularity and also defines the limiting case of counterexamples theorem, where you have a measure in the right-hand side. Okay, I think this is a good time to stop, and we can say more about tomorrow. Thank you. Questions, remarks, complaints? No. Insults? No.
So you were proceeding with the equality ideas and exceeded Caccioppoli.
Huh? It was independently. Because essentially the idea was different. The idea is that I wanted to prove. I get an equation like this, which is local, and then you want to prove a point. Okay, I can tell you what is. It's very easy to say. Okay. Okay, how can you estimate the gradient of this guy? This is less than or equal than I1 of mu. That's the reach potential. Classical. This comes from the fundamental solutions. Okay, take p equals to 2, but now take a nonlinear problem. So how can you estimate mu? So there's no fundamental solution, but you can prove the same thing, exactly the same thing. So now you want to, how do you proceed in doing this? You differentiate the equation. But you cannot differentiate in a standard way. You can you do the fractional derivatives, and then you make a fractional and using it?
I mean, with this x minus y, with the integral operator, you like differentiate in that sense.
Yeah. And then you write a fractional Caccioppoli type inequality, and then you run a fractional Giuseppe style. Caffarelli and Vasseur have a fractional operator.
Yeah.
So the Caccioppoli inequality, which is the hard part there, because the problem is local and you no longer have inequality, then comes easily there, because the problem is already fractional. Then we start the fractional Giorgi. So from that point on, but the overall idea is that you run.
So I'll go this week.
Yeah. And the point is that this fractional derivative cannot be written pointwise. So you need to make it no longer. But it's and then I discovered that in this there was a similar approach.
I have told you American multiplication on my
Tu hai detto prima,
So,
la decomposizione della seminoma di Caccioppoli che fa saltare fuori una misura nella parte non locale, mi sono due slide. Esce fuori una misura non della falla, del genere, possibile?
Cioè? No, scrivo un po'.
Due slide prima mi sembra c'era una formula che ancora è questa qua, questa misura qua è data al bordo di un, cioè cosa sarebbe?
No, questo è locale, questo è locale.
Ok, ma per il caso non locale esiste una formula simile anche?
so I am not
Tipo
Questa,
che-
guarda, stiamo facendo l'analogo di questo col Como e Yannick, ma dovrebbe esistere una cosa.
Ma c'è una richiesta tipo della dimensione, la dimensione dove è concentrata la misura mu?
Io sì.
Nessuna, neanche di capacità.
So that's it.
Ah, ok, grazie.
Questa è l'analisi frazionaria prima di proliferazione.
No. Perché se la misura la poni tipo si pone su.
You want to know? But my voice is like
Even better.
What do you expect?
La misura si mette su insieme a capacità.
No, questa è, vabbè, poi viene quello che viene.
Ah, ok, va bene, non so quello,
Poi viene quello che viene, sì.
Va bene, ok, grazie.
Figurati.